welcome back to Tripplikit and to part 3 of the synthesis tutorial which accompanies the build of the Tripplikit mean green synthesizer. Firstly, just a note, a lot of the audio effects I'll be talking about are quite subtle and can be lost in YouTube's processing, so the examples I give and the code that generated them are available to download. See the link in the description for this video. Okay, the mean green is an oscillator based synthesizer, not a sample based synthesizer. So why are we looking at sampling? Well, the original analog synthesizers did in fact have circuits in them which oscillated, which was how they created their waveforms. Digital synthesizers, on the other hand, generate their waveforms, and in our case we're going to be generating our waveform using single cycle samples. So that's why we're looking at sampling. All the things that modern samplers do can be done using audio tape, and in fact the Mellotron was a sample-based synthesizer which used lengths of audio tape. The advantage of digital sampling, however, is that something that would take hours of cutting and splicing and re-recording using audio tape can be done on the fly in the digital domain. What's more, this doesn't actually use a great deal of processing power, and this ability gave rise to the modern digital sampler. In this tutorial we're going to look at two aspects of sampling, the two most basic aspects. Firstly, the ability to take a sound recording and cut it up and play it back in a different order and loop it. And then secondly, we're going to look at the ability to play our sound recording back at different pitches and indeed variable pitches. Okay, here we have a digital recording, a sample.
Welcome to Tripplikit, home of interesting electronics.
So let's chop it into several bits and loop one of them.
Welcome.
This is pretty straightforward to do in the digital domain, simply a matter of setting the read point of the sample to where we want it. There is a link in the description for the video to download the code and have a look at it.
Welcome.
Hang on though, there's a nasty click in that loop. Let's find out why. Okay, we've zoomed in here to where the loop loops round. It comes from the end of the loop to the beginning of the loop, and we can see the end of the loop is a negative value and the start of the loop is a positive value. The result is a loud click at the join. To get round this, we pick the start and end of our loop so that they line up. This is usually as the sample crosses 0. So to avoid the click, we should start our loop here and end it here. So here's the same example as bit above, but I've carefully chosen the start and end points so they line up.
Welcome.
If we zoom in, you can see there is no level change and hence no nasty click. However, the fact that the slope changes abruptly does introduce a slight click, which shows up on the spectral view. However, this is generally not noticeable, and samplers usually have software built in to automatically find the 0 crossing points for you. And here it all is, chopped up, reordered and looped.
Electronics, interesting home of Tripplikit. Welcome.
Okay, another way to avoid clicking when switching between sample portions is to crossfade between the start of one sample and the end of another, or for looping between the start and end of the loop. Now, up to now we've been switching abruptly between the ending sample and the new sample that's starting at the point shown by the dashed line. For crossfading, we need to allow a bit extra of the ending sample or the end of the loop, so this can be faded out over the crossfade period. Meanwhile, the new starting sample or start of the loop is faded in, leaving the overall level unchanged. This crossfade period is typically 20 milliseconds. The advantage of this is we can switch between samples or loop at any point regardless of zero crossings. The disadvantage is that the processor power required increases as we are playing two samples, and also a need to apply the crossfade. So in this example I've taken a series of samples from my original recording, each one of just under half a second long, and each of them starting a 1/16 of a second after the last one. I've then put these one after another, crossfading between them to produce the sound file you're about to hear, despite the fact I've paid no attention to where the samples start and end.
Welcome to Tripplikit, home of interesting electronics.
There you go, chart bound if I'm any judge. Another important thing we want to do with sample sound is to change its playback pitch stroke speed. Okay, let's do something very crude to start with and take every other sample value from our recording. Here's the original.
Welcome to Tripplikit, home of interesting electronics.
And here's one where we've taken every other sample.
Welcome to Tripplikit, home of interesting electronics.
Okay, that sounds twice as fast and an octave higher. Okay, now let's take our original recording and repeat every sample.
Welcome to Tripplikit, home of interesting electronics.
Note that in both cases the pitch and the speed are linked. Increase the pitch and the sample plays faster, decrease the pitch and the sample plays slower. This is not a problem in our case actually, because we're using single waveform samples that we can repeat as often as we need. Okay, so we've played our sample at twice and half the original frequency, but what if we want to be able to play it back at any frequency? So here we have a section of waveform which we've sampled, the samples being represented by the green dots, and we've numbered them for convenience. Let's say we want to play this sample back at 1.3 times the original frequency. Our output samples would now be the blue dots, which represent the sample points at 1.3, 2.6, 3.9, 5.2, 6.5, etc, etc. Unfortunately, we don't have waveform values for those points. Instead, we have to interpolate an approximation for these values, and we do this as follows. Here, for example, we are looking at sample point 3.7 of our waveform. We're actually going to interpolate it from values y3 and y4 at sample points 3 and 4.
because these are the only values we have to work with. We have no idea what the waveform does between these 2 points, so all we can do is simply assume it's a straight line. So the value we will output is actually going to be the crosshatched blue dot instead of the actual blue dot on the curve. So what's the value of y at the hatched blue dot? Well, because we're assuming a straight line between the 2 samples, y is very simply calculated from this equation. Notice that although our fractional sample number is 0.7, we take 0.7 of the higher sample number, not the lower. As you can see, this calculation will result in an error, and this error will show up in our audio output as noise. So, what we want to know now is how much noise this noise will be, and will it be acceptably small. To get some idea of the noise introduced from interpolating a sample to generate different frequencies, we're going to look at the simplest possible waveform, a sine wave. We'll look at more complex waveforms in the next tutorial when we come to look at the oscillator design in detail. In this case, our sample actually only needs to be 1 cycle long, because when we get to the end of it we can round back to the start again. I'll describe how this works in detail in the next tutorial. I tend to refer to these single cycle samples as wavetables rather than samples. Okay, I've plotted one out here on this spreadsheet. This one is 64 samples long and was generated using this equation. Since I'm working on the computer, I'm using floating point values here. The advantage of using a sine wave is that we can calculate our intermediate values to check our interpolated value against. So let's consider the case of sample number 2.5. The table values for samples 2 and 3 are calculated here. And here is the interpolated value for sample 2.5. Finally, here is the actual value for sample 2.5, calculated from the original equation. By comparing the two, we can see that our error in our interpolated value is about 0.0003. And we'll take an average and a root mean square, an RMS value for these errors when we come to test the table out. As I've said, this error represents noise, and we want to know how the noise generated is affected by the frequency of the waveform we are outputting, and we also want to know how the size of the wavetable affects the amount of noise generated. To investigate this, I've written some test code which uses a wavetable to output a sine wave which gradually increases in pitch over the frequency range we might want an oscillator to operate. This results in a sound file that starts like this, is like this in the middle, and ends like this. Yeah, I know you don't want to listen to 3 minutes of sine wave. Okay, I'll run this for 4 different table sizes and record the average noise for each. Takes a few seconds to generate each sound file because they're 3 minutes and a bit long. Okay, for each run we can see here on the first line it tells us the size of the table, and on the second line it tells us the average noise in samples and then in dB. So for the 64 value table the noise is 19 samples or minus 64 dB. The 128 sample table the noise is 4 samples or minus 76 dB. For the 256 sample table the noise is only 1 sample or minus 88 dB. And for the 512 sample table the noise is 0 samples or minus 100 dB. So as you can see, if we use tables of 512 samples, the noise due to interpolation is less than the quantization noise, which is minus 96 dB. Now I thought the noise generated from interpolation would be heavily frequency dependent, but it turns out it is not. This sound file is the noise from running the 64 sample table test. I've multiplied the noise values by 100 so we can hear them and see them, and as you can see the amplitude of the noise remains constant as the frequency sweeps up. As I say, I didn't expect that at all. Okay, looking at the spectrum and listening to it, shall we start there? We can see our noise is fairly typical digital noise, the sort of thing we're trying to be very careful to avoid. Okay, so now we are in a position to use wavetables as the basis of an oscillator, and in the next tutorial I will be writing and testing the actual oscillator code we will be using in the mean green. So until then, it's goodbye from Tripplikit, home of interesting electronics.